Joshua sir, we'll start the program.
Yes, we shall start.
Okay, sir. Okay.
Welcome to George M. Thomas Memorial Lecture 2020-21. I request all the participants to keep your mind.
Dr. George M. Thomas was the principal of Cms College from 1965 to 1977. He joined the physics department.
I can hear.
After obtaining his doctorate degree in nuclear physics.
I think we lost the announcer.
We know sound has lost.
It was under Dr. George M. Thomas that Department of Physics initiated its postgraduate program. His passion for physics pervaded his whole life. He was the teacher of the renowned scientist Dr. Qcd Sudarshan. Our department enjoyed remarkable progress during the tenure of Dr. George M. Thomas. Let us start our GMT Memorial Lecture 2020-21 with a word of prayer. I invite the Bursar of CMS College, Reverend Jacob George, for leading us in prayer.
Let us pray. Eternal God, our Heavenly Father, we thank you for the day in which we are gathering together from near and far. Lord, the seat of all wisdom and knowledge. In your grace, you enlighten our mind and thought with your wisdom. Thank you, Lord, for providing us gurus, teachers, and institutions. Impart that knowledge to our end. Today we especially pray for the seminar for which we gathered together. Let all the participants be blessed with knowledge and new insights. Lord, we pray for today's resource person, Mr. Rene Irwin, that he be especially blessed by your grace. Now, Lord, you remember the life, stories, and contributions of Dr. George M. Thomas, who served this institution as principal and secretary of Department of Physics. Lord, we pray for the people who are organizing this seminar. We pray for the Department of Physics, HOD, teachers, and students. We give all in your mighty hand, that all will have a very meaningful and wonderful time here. We ask this in the precious name of our Lord and Savior Christ. Amen.
Thank you, Reverend. Now I request Dr. Renu Jacob, the head of the Physics Department, CMS College, for the welcome speech.
Respected Principal Dr. C. Joshua, Bursar of CMS College, Reverend Jacob George, distinguished guests, teachers, and my dear students. A very warm good morning to all. It's a moment of great honor and privilege for me to extend warm welcome to all of you on this memorable event of Dr. George M. Thomas Lecture 2021. Dr. George M. Thomas, former principal and head of the Department of Physics, was one of the brilliant academicians CMS College has ever witnessed. Department of Physics has attained remarkable progress during his tenure. The George M. Thomas Endowment Trust, framed in 1992 by the faculties of Physics Department, was not just to honor the life and works of their dear professor, but to continue his vision in promoting a scientific arena focusing on the developments of physics and future trends. At this onset, let me welcome the respected principal of CMS College, Dr. C. Joshua. Sir is always encouraging and supporting to all our department activities with great understanding and care. On behalf of Department of Physics and GMT Endowment Trust, with all respect, let me welcome Dr. Verghese Joshua to this program. I am much privileged to welcome the bursar of CMS College, Reverend Jacob George. Reverend Jacob George is always enthusiastic in helping us in all our department activities with utmost concern. So with great privilege, let me welcome Reverend Jacob George on behalf of Department of Physics and GMT Endowment Trust. CMS College and Department of Physics are much honored today with the presence of Professor Rene Belvide as a guest speaker for GMT Lecture 2021. We thank you for accepting our invitation despite your tight schedule. Professor Rene Belvide, MD Anderson Chair Professor of University of Houston, is a familiar name to the scientific community. Professor Belvide is a leading experimental nuclear physicist working at Large Hadron Collider at CERN and Realistic Heavy Ion Collider at New York. It's really a great opportunity for all of us to listen to a nuclear physicist when we actually commemorate the life and works of Dr. George M. Thomas, who himself was a nuclear physicist. So with all respect, honor, and privilege, let me welcome Professor Rene Belvide to CMS College and Department of Physics. I would also like to extend my happiness in welcoming our senior teachers to this program. They guide us in all possible ways, taking the leading roles. We are ever grateful for their love and we need your blessings and guidance always. Warm welcome to all our senior teachers. It gives me immense pleasure and joy to welcome our senior alumni members to this program. They always gives us a deep sense of care and support in all our department activities. Few of our distinguished alumni members are attending this program. May I warmly welcome the former Vice Chancellor of Cochin University and our distinguished alumni, Dr. Babu K. Joseph sir, to this program. Also, I specially mention Professor Ummen K. Verghese sir, distinguished alumni and ranked as a top 10 material scientist in the world. Sir introduced Professor Rene Belvide to us. Professor Ummen took all the efforts in finding a suitable person as a guest speaker for us today. So with great pride and joy, I welcome dear Ummen sir to this program. I also like to welcome our teachers of physics department, teachers from other department and other colleges as well. Also extending my happiness in welcoming all my dear students to this program. Wishing a great day ahead. Thank you.
Thank you, Dr. Renu. Let me welcome the principal of CMS College, Dr. Verghese Joshua, for the presidential address.
Professor Rene Belvide, the speaker and the chief guest today. Professor Babu Joseph, former Vice Chancellor of Cochin University of Science and Technology. Professor Ummen K. Verghese, our beloved alumni. Reverend Jacob George, bursar of CMS College. Dr. Renu Jacob, Head of Department of Physics. Faculty members, former faculty members, distinguished guests, and my dear students. Good morning to all of you. It is an honor to address you all on this beautiful occasion.
This phenomenon is called photoelectric effect.
The 18th Dr. George M. Thomas Endowment Lecture of this year. The COVID-19 pandemic has been a great equalizer for all. And I think it is a global event which simultaneously affected all the people in the world. As expected in a time of global crisis with no clear end date, the most important traits are adaptability and resilience. Even though the pandemic crippled our regular functioning in due time, we were able to successfully shift to online mode. And it is giving me immense pleasure to witness each and every department of CMS College, especially the Department of Physics, working towards this goal by actively engaging with all their departmental activities, despite being in unprecedented time. And the way they have coordinated and executed this year's the Dr. George Thomas Endowment Lecture is an absolute marvel. Dr. George Thomas joined CMS College family in 1992, in the physics, 1952, 58, and became the 20th principal of CMS College in 1965. And he was one of the modern age-top academicians of the country, a renowned physicist and scientist whose visions laid the foundation to one of the best physics departments, one of the best departments of the college. And the George Thomas Endowment Trust was formed in 1992 to honor these great academicians' contributions, particularly to the college. And there are several activities planned and executed under the trust to benefit, especially to young scholars and academicians. And the Dr. George Thomas Endowment Lecture is one of such prestigious programs conducted annually by the Department of Physics of CMS College with invited speakers in physics research and education. This year, we are so honored to have Professor Rene Belvich, MD Anderson Chair, Professor Houston College of Natural Science and Mathematics. And his field of research is relativistic heavy ion physics, which is a specialized subfield of nuclear physics. Scientists have long hypothesized the existence of strange matter in the core of neutron stars, which are considered to be the smallest and the densest stars in the galaxy. And Professor Rene Belvich is searching for that elusive strange matter to understand what role it played in the evolution of the universe. And funded by more than $2 million, I think so, from the US government or the Department of Energy. Belvich is collaborating with his fellow professors and scientists to figure out how the transition from plasma to existing matter occurs. Just as you all, I am also excited to listen to his talk on the topic, the creation of matter in the universe, colliding heavy ions at the speed of light. I am also happy to extend a warm welcome to Professor Belvich to CMS College once again. Before we lend our ears to him, I want to congratulate the Department of Physics and the members of the faculty for coordinating this event with a fabulous speaker. And I would also like to thank Professor Umman K. Varghese, our beloved, one of our beloved alumni who makes this event possible and brings Professor this fabulous speaker to this particular event. And I'm happy to see the presence of Professor Babu Joseph, one of our great alumni, and I also extend a warm welcome to you, sir. And I wish all success to this particular talk today. Have a nice day. Thank you.
Thank you, sir, for your support. Now I invite Professor Babu K. Joseph, a distinguished alumni and former Vice Chancellor of Cochin University, to share a few words about Dr. George M. Thomas.
Thank you for inviting me to say a few words about my great guru, Professor George M. Thomas. who taught me almost 61 years ago. I still remember him with vivid colors, with Professor standing on the platform facing us and teaching nuclear physics. I don't want to say many words of formality on this occasion because of the limited time. So I will say a few words about Professor John Thomas. When I joined CMS College for my undergraduate program way back in 1958, he was not there. The department had been headed by Reverend Casey Matthew, and there were faculty members like Professor Casey Chapo and others. In 1960, Professor George Thomas returned from McGill University, Canada. He had been on study leave for a few years from the college. His field of research happens to be nuclear physics and particularly radioactivity. I think he studied beta radioactivity in some nuclides. He brought a fresh air of interest to faculty and students of the department. I remember his teaching methods. It was different from the methods followed by other teachers. He had been influenced by his exposure in Canada. So he made us work out problems by ourselves. This was a new experience for us. He forced us to think for ourselves. Well, I don't remember him as an administrator in the capacity of principal because I left college before he became the principal. However, he was the head of the department for a year or two when I was there. Later on, I used to meet him whenever I passed through Kottayam for his advice. So, that I continued even when I was doing my PhD after my master's program. He one day told me that he had started writing popular books on science in Malayalam. Unfortunately, today's guest speaker cannot understand Malayalam, so I don't want to say anything about it, apart from the fact that his books were very interesting. They were mainly addressed to high school and middle school students. One of the titles that I remember is Adithatyal Anayam Veedu. That means if an elephant falters in its steps, it will collapse. That's the meaning of the Malayalam title Adithatyal Anayam Veedu. He gave me a copy of that book, his book, with his characteristic smile, which I still cherish. Since my time is limited, I would once again place on record my deep appreciation of Professor George Thomas, who happens to be a teacher of Professor Qcd Sudarshan also. Professor Qcd Sudarshan did his intermediate, that is the 2-year program after high school. He was taught by Professor Jordan Thomas. He was taught physics particularly, and he was taught mathematics by another distinguished professor of CMS College, Professor Epen. Once Professor Sudarshan remarked to me that but for Professor Jordan Thomas, he would not have studied physics. So he was the Professor George Thomas was the person who inspired ECG Sudarshan that early in his life. On this occasion, I join you in commemorating Professor George M. Thomas and pay homage to him. Thank you.
C. Thomas, Faculty of Physics Department, will be introducing a guest speaker.
Good morning. Am I audible? Am I audible?
Yes, Prima. Yes, yes.
The Department of Physics, CMS College, is honored to have Dr. Rennie Welby with us. And with great pleasure and humbleness, let me introduce you, sir. Rennie Welby is a distinguished MD Anderson Professor of Physics at the University of Houston, USA. Dr. Welby received his PhD from the Johannes Gutenberg University in Mainz, Germany in 1989. He leads the experimental nuclear physics effort at the University of Houston, which is involved in the STAR experiment at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, New York, and the ALICE experiment at the Large Hadron Collider at CERN in Geneva, Switzerland. He is presently the chair of the Texas section of the American Physical Society and a member of the Sigma Psi Honor Society. He has to his credit 1,000 peer-reviewed papers that gathered over 85,000 citations, and his H index is 151 according to Google Scholar. Let me now put light upon some of the main works of Dr. Welby. The early predictions of the formation of a new state of matter, quark-gluon plasma, has now been unequivocally vocally confirmed by the RHIC and super-proton synchrotron experiments. The discovery phase is behind, leading to the surprise finding of a strongly coupled state of deconfined quarks and gluons termed quark soup in a recent Scientific American article, and are embarking on a journey to characterize the seemingly very surprising features of this new state of matter. The main interest now lies in the interdisciplinary research on the QGP, which recently brought together scientists from string theory, plasma physics, astrophysics, high energy and nuclear physics to understand the discoveries at RHIC, which might have implications on a macroscopic scale for the evolution of the universe and on a microscopic scale for the understanding of quantum chromodynamics. The LHC will be a major step forward by allowing to probe the quark-gluon state at energies 30 times higher than RHIC. ALICE will be the most versatile heavy ion detector at the LHC, and looking forward to using the detector to determine properties of the QGP in order to understand the origin of matter in the universe. Title of his today's talk is The Creation of Matter in the Universe, Colliding Heavy Ions at the Speed of Light. It's a great privilege, sir, to have you with us. We are all eagerly waiting to listen to you. Please, sir.
Well, thank you very, very much.
Thank you, Dr. Prima. Now it is the time for our GMT lecture. I request Professor Rennie Welby to take over.
Okay. Thank you very much, and I hope you can all hear me. I am very honored and humbled, and it will be a great pleasure for me to give this talk today. I'm going to share my slides and see that this works, and then if you tell me that you can see what I will show you, then we will move on. You should be able to see my slide. Is that correct?
Yes, sir. Yes, sir.
Very good. Very good.
Yes. Thanks.
So let me thank you again. The title of my talk is The Creation of Matter in the Universe. And we're doing this by colliding heavy ions very, very close to the speed of light. And what you see here in the background is actually not just a picture. It is a depiction of the temperature in the whole universe at this point. So this is the cosmic microwave background, which on average is on the order of 4 Kelvin. And what you see here in the dark and light spots is effectively the temperature variation that we see right now in the universe. But it's a little misleading. It looks like it's very structured, but it is not. It is very homogeneous, and the deviations that you see here on the microkelvin level. So the universe has expanded to this size that it has now and the temperature that it has now from a single point. And we believe that the idea of having a Big Bang and then following the matter through the standard model of physics is a valid and good idea, and it is at the heart of my talk. Before I go into the details, I actually have some connections to Kottayam that I personally was not even aware of. I was certainly aware of the fact that my colleague, Dr. Uman Varghese, is a good friend here at the University of Houston. But I also spent a year and a half at UT Austin in 2007. And one of the people that I met there a lot and had a lot of discussion with was Dr. George Surdershan. And I have to admit myself that I was not fully aware that he was actually from Kottayam at the time. We had a lot of coffee together. And this is a famous picture that is also on his Wikipedia page, actually, which shows him drinking a coffee. I think the picture was taken a few years after I met him in 2007. And it's an interesting story because one of my early mentors was Professor Roy Glauber. And when I told Roy that I would go to Texas for a sabbatical, he says, sit down with George. If you sit down with George, you can learn a lot of physics. And when I looked a little bit into it, Roy Glauber had won the Nobel Prize 2 years earlier, which is a Nobel Prize that should have probably also gone, at least in addition to Roy, also to George Surdershan, because he got the Nobel Prize for the Glauber-Surdershan representation. And when I met George, I talked to him about it, and I already realized the grace that he is carrying. He was not bitter about it. He was not upset about it. And I learned a lot of physics from him. And one of the things that I said to him was that, you know, before I talked to him, I learned a lot of physics from Roy Glauber. And George looked at me and he said, you can learn a lot of physics from Roy, but you will never learn as much physics from him as I learned from my mentor, Dr. Thomas at Kottayam. So I forgot the whole story. It's 10 years later. And then Uman came to me and said, are you interested in giving this endowment lecture? And then it dawned on me that we're actually talking about the same George Thomas that George Surdershan and I had talked about 10 years ago in UT Austin. And now that both Georges have passed on, I think one thing that I would like to get across in my presentation today is that both Drs. Thomas and Surdershan would be proud to see how far nuclear physics has come in gaining a very deep understanding of the creation of matter through the experiments and through the theory that has been performed in the last 2 decades, let's say. In order to do this type of physics that has to do with creation of matter very, very close to the Big Bang, you have to accelerate particles to very, very close to the speed of light. And this goes generally through very large accelerator facilities at any given point in time. Generally, one is running and one is phasing out. So I had the privilege over the last 25 years, almost 30 years now, to be a very active member at both big facilities. And RIC is still running because it has the opportunity to add a new unique feature to the phase diagram that I will show you later on. but the big machine at the moment is certainly the Large Hadron Collider at CERN. So I show you the two machines here. In 2000, we started running at RIC. It's a 2.5-mile circumference ring. In America, you have the privilege of finding a lot of land that is not very populated. So this is a ring on Long Island that is above ground, and it's actually so large that you can see it from the space station. There's the little ring on Long Island that is the RIC Accelerator, which has a 2.4-mile circumference, and it accelerates particles, heavy ions, up to 99.995% the speed of light. 10 years later, we initiated beams at the Large Hadron Collider. You are in Europe, you don't have the privilege to be above ground, you're actually below the city of Geneva. You see here, and I don't know whether you can see my pointer, but on the one side here, where it says LHCb, that is actually the Geneva airport, and you see the 17-mile circumference ring, and you see 4 interaction regions. CMS, LHCb, Atlas, and Alice are the 4 experiments, and the heavy ions are mostly done by the Alice experiment, and that's the experiment that I will talk to you about today mostly. So the difference is that you go from 200 giga-electron-volts energy to 5 tera-electron-volts energy, and you see what happens to the speed of light. You know, I don't read the number off, but you get a few more decimal points to get closer to the speed of light, and that makes a difference in generating this new elusive phase of matter, which we call the quark-gluon plasma. If you cannot hear me, or if you have problems with the slides, please interrupt me so that I know that we're
Renee, can you reduce the size a little bit because the right side is cut.
The right side is cut. Let me see. I'm at the same setting that I was before. So let me see.
Yeah, you can try now.
Let me see this. Let me try this. How does this look?
No, I think it's still the right side is outside this frame.
I mean, we did it by moving this around, so I'm trying to do the same thing again.
Yeah, I think this one should be better now.
How's this?
Better, much better. Yeah, yeah, I think we can almost 95% we can see now. That's fine.
Good enough, or?
Yeah, I think it's good enough.
Okay. Okay. Yeah, I don't want you to miss something because I worked a lot on the slide. So you see the 2 accelerators going from RIC to the Large Hadron Collider. Now here are the 2 experiments. So on the left-hand side is STAR at RIC, and on the right-hand side is the ALICE at the Large Hadron Collider. The experiments are very, very similar. Cylindrical experiments having many, many subsystems in order to capture most of the physics that you can envision. The cost is slightly different. The STAR was about a $50 million detector. The ALICE was about a $250 million detector. So technology has moved on, but in the end, the results that you can achieve are complementary to each other, but they also kind of, you know, try to have some overlap so that you can see that things that we see that are very spectacular can be confirmed by other experiments. STAR, about the size of a cricket field. I thought if I talk to Indians, they know what a cricket field is, so I think that's the right size measure for my Indian audience. And also the weight of ALICE is the weight of the Eiffel Tower. Most of this sits in the magnets, obviously, that are surrounding the whole experiment. So here the magnets are in blue, and here the magnets are in red, and you see these are massive, massive magnets. Not superconducting. The superconducting magnets are always in the ring. In both cases, in STAR and in ALICE, the ring has superconducting magnets. The experiments do not have a superconducting magnet. And in order to do physics, this is a worldwide operation. STAR, 800 collaborators from 14 nations. ALICE, 2,000 collaborators from 39 nations. And if you look at the nation distribution, you will see that India is very strong in this field. You have 8 institutions from India in STAR. You have 14 institutions from India in ALICE. And also India became an official member state of CERN in 2018. So very, very strong contingent from our Indian friends, large groups. The contingent right now in ALICE from India is larger than the one from the United States. So that is something to be proud of. Very interesting physics is being done. What are we doing? We're looking at the first second of the universe, and if you go into any textbook, you will see that a lot happens in the first second of the universe. And generally, you can look at this as a function of time, or you can look at it as a function of decreasing temperature. So when you compress our universe, which is at 4 Kelvin right now, down to a single point, you can determine the energy density that single point will carry. And out of that energy density, you can calculate a temperature. The scale for our temperatures is mega electron volt. I show you later on a picture that translates that into Kelvin, and then you can see what kind of temperatures we're talking about. But generally speaking, there are a lot of transitions happening because we still believe that the 4 fundamental forces have been unified at the Planck scale. But then when you go away from the Planck scale, when you open up the universe, these forces will decouple from each other. And generally, when they decouple from each other, they go through a phase transition. So the first one you would probably hit, besides decoupling gravitation, which happens at a scale that we will never be able to reach, the first one you will hit is the electroweak transition, and which is carried by high energy physics, and the discovery of the Higgs boson gives you also the scale of where you can do this. You can do this in the Large Hadron Collider, but you can only do it with proton-proton collision. The next transition is the transition that I'm interested in, which is covered through nuclear physics, which is the Qcd phase transition. And I'll show you much more about this soon. And then when you go even further out into the minute range in terms of the time scale since the Big Bang, you hit here and here what's called Big Bang nucleosynthesis, and that is often dealt with by astrophysical measurements, but also nuclear physics measurements with radioactive beams, which become popular right now at other facilities that I will talk about at the very end of my talk. So I am interested in this Qcd phase transition, which we think happened a few microseconds after the Big Bang, somewhere between 10 to the minus 3 and 10 to the minus 6 seconds, and at a temperature of about 200 MeV. And if you want to put this in a nice color picture, you see here that you're starting off, you're going down, you hit this quark hadron phase transition, this Qcd phase transition at about a microsecond, and then you go on to nucleosynthesis, to matter domination, to atomic recombination, galaxy formation, all the way up to today, 14 billion years later. So by colliding these heavy ions, we think we can go back in time to about a microsecond after the Big Bang. And this was a very early picture, and I'm just showing it to you here because rather than showing you the temperatures in mega electron volts, I show you in degrees Kelvin. So this Qcd phase transition happens at about a few times 10 to the 12 Kelvin. And you can translate that into temperatures that you can compare to the core of the sun, and it's 150,000 times the core of the sun in terms of temperature. If you look at this again in terms of phase transitions, you see that this third phase transition would be the one where quarks and gluons confine into hadrons, into the matter that we know of right now in the universe, the visible matter, protons, neutrons, electrons, and so on. And before you had the electroweak phase transition, and before at the Planck scale, you had the grand unified theory. So this is the range that we can address with nuclear physics. And we have actually a series of facilities, not only already there, but also planned. So RIC and LHC are running right now. NICA at Dubna in Russia will start in about 2 years from now. And FAIR at the GSI in Darmstadt will all start in about 4 years from now to run at slightly lower energies. And why we are interested in slightly lower energies, I show you in one of the next slides. If you go even lower in energy, you have other facilities like the radioactive beam facility at Michigan State University, which will start in about 2 years from now as well, that measure nuclear synthesis. And that is also an important and interesting part in the evolution of the universe, and we're looking forward to their results as well. Here's a phase diagram, and what you're used to when we talk about phase diagrams is the phase diagram of water. So you have essentially a PT diagram, pressure versus temperature, and it's the same here. So instead of having, steam, water, and ice, what you have here is a gas of hadrons in the lower right left-hand corner here. And that the gas of hadrons is supposed at a higher temperature or a higher density too to go into a plasma state of deconfined quarks and gluons, free quarks and gluons. And the interesting thing that has happened over the last few years is that we get now information about this postulated phase transition line, not only from very high energies at the Large Hadron Collider and the RIC facility, but also lower energies at the RIC facility, and that's why it's still running after almost 20 years. It goes to lower energies because it might be able to prove that, as in the phase transition diagram of water, there's also a possible critical point in the phase transition diagram of quantum chromodynamics. And the other thing that has gotten us very excited is that the energies that can be reached if you let RIC run not as a collider, but in a fixed target mode, where you shoot just one beam against the target, the energies that are reached here are becoming very similar to the energies that you reach when you have a merger of neutron stars that generate a gravitational wave signal measured by LIGO and Virgo over the last 2 years. So we suddenly have the opportunity to map this whole phase diagram and potentially that postulated transition line all the way down from the hottest matter in an accelerator to the coldest matter at the core of a neutron star. And you see, when you go to a neutron star, the matter becomes cold, but very, very dense. So what I'm plotting here on the x-axis is what we call the baryon chemical potential, but just imagine it's the density of protons and neutrons inside the fireball that you're generating. So the denser it becomes, the more these protons and neutrons lie on top of each other, the more you walk up this scale. And the neutron stars are very, very dense. The density, the mass of the sun with the right Lagrangian on the right configurations, we're very certain that they give good guidance to what should happen during the phase transition. But if you want to do it purely experimentally, you have to create this system now of a quark-gluon plasma, and you have to step through the phase transition, not from below into the quark-gluon phase, but from above out of the quark-gluon phase. And you have to measure what happens, A, in the phase itself, and B, what happens when you go through the phase transition. So in the early days, we always called that, do we come out the same way we went in? What are the different degrees of freedom? What type of matter is made during this phase transition in the laboratory that can tell us something about the matter that existed in the universe about a microsecond after the Big Bang? And we know that it is certainly different than the things we're looking at now that have survived for 14 billion years and that are pretty much exclusively made out of neutrons, protons, and electrons. So we want to see what else is there. That was the whole idea. The problem in doing that is that quantum chromodynamics is very, very different from quantum electrodynamics. So here's a typical quantum electrodynamics example. I hope you can see the electron nicely circulating around the nucleon. This is the typical structure of an atom. It's neutral. And if you want to study quantum electrodynamics, the only thing you really have to do is to separate the positive from the negative charge. And you do that, you can do that because the force that you're feeling falls off with 1 over r squared. So you can easily pull an electron away from the nucleus, and then you can study the electron separately from the proton and the neutron. And by doing that, you have a really good understanding of quantum electrodynamics, of how charges interacting with each other. And it is due to the fact that the force holding them together is a 1 over r squared law, Coulomb's law, as much as gravitational law. It's a typical law of physics. The not so typical law of physics is quantum chromodynamics. You have a color neutral state, so-called white proton, made out of 3 quarks of different color. And now, if you look at the picture above, you would say, okay, if I can pull one of those quarks out and study it, I should be able to learn a lot about quantum chromodynamics. The problem is, the way you do this is you would excite those 3 quarks, and when you excite them, you pull them apart. But when you pull them apart, the problem is the force, the color force, is actually proportional to the distance rather than inverse proportional to the distance squares. That means the force grows with separation. It acts like a rubber band effectively. The more you pull on it, the more force you have. That force gets so big that that force can generate a quark-antiquark pair out of the vacuum. When you do that, what you get is that the quark will go back to the white proton, and the antiquark will pair with the quark that you have pulled away to a white meson. So you cannot break confinement by pulling quarks apart. And that is a very big problem because you cannot make the force stronger by separating the quarks. So in order to separate the quarks, you go the other direction. You make the density very, very high, and you hope you reach a distance between the quarks where the strong interaction is asymptotically weak. So we know that the coupling constant gets smaller and smaller and smaller the closer the quarks are together. So you want to reach very high density of quarks, and you do it in 2 ways. First, you heat it, and you see when you heat it, I go back and forth between those plots. When you heat it, the energy that you put in generates quark-antiquark pairs. It generates mesons that are made out of quarks and antiquarks. But overall, if you look at this picture and this picture, what it does is it generates more quarks over the same volume. And then you compress it. And if you compress it enough, you can see now that the quarks inside do not know anymore which white proton they belong to because they're all on top of each other. And through heating and compression, you have effectively deconfined the color matter into a quark-gluon plasma. It doesn't want to be in that state. It doesn't like that state. As soon as it can expand, it will expand. And as soon as it expands, it will go back into color neutral matter, but not the same color neutral matter that you started off with, because you added quarks to it and you added enough energy to it that it can make quarks that weren't there before, that it can make strange quarks, charm quarks, bottom quarks that were not in the original neutrons and protons that you were actually accelerating. And on the lattice, this looks like this. This is a plot of a phase transition measuring the energy density as a function of temperature, and you see what happens. The energy density as a function of temperature goes through a phase transition. It doesn't go through a first order phase transition. It's not discontinuous. It doesn't even go through a second order phase transition. It goes through a so-called crossover phase transition, so that the curve is relatively smooth. But clearly the number of degrees of freedom changes from a hadronic system to a system of quarks and gluons, where the number of degrees of freedom goes up by about a factor 6. And it does that as a particular temperature and at a particular density. And if you look at that, you essentially go from a confined system here to a deconfined system here. And if you look at the scale is about 130,000 times the temperature of the core of the sun. So you're getting a very, very microscopic system that is extremely hot, hotter than anything we've ever made on Earth, and has a very, very high energy density, more dense in terms of energy than anything we've ever made on this planet. So the way you do this is with an accelerator, and this is a beautiful example how you can build accelerator upon an accelerator. This is the relativistic heavy ion collider at RIC. This tandem here, which was a linear accelerator, was built in 1955. And then every time we wanted to go up in energy, we built an additional part. First, the alternate gradient synchrotron, then the booster for the alternate gradient synchrotron. We did fixed target experiments in the 90s in these halls here. I hope you can see my pointer. And then we started building a collider experiment. So rather than shooting a beam onto a fixed target, you let beams go in clockwise and counterclockwise. So if you follow my little arrow here, my little point, you see there is what we call the blue and the yellow ring. The yellow ring is counterclockwise, the blue ring is clockwise, and there are 4 regions where you kick the 2 beams up so that they cross each other. And in the regions where you kick those beams up so that they cross each other, you build 4 big experiments: Star, Phoenix, Phobos, and Brahms. That was 20 years ago. At this point, only Star is still running, and this machine is getting ready to be converted into an electron-ion collider in about 10 years from now for new experiments. But for the next 5-6 years, we still hope to run the Star experiment. The real feat, I would say personally, and I have to humbly admit this, the real feat of these things is not the experiments. The real feat is the accelerator itself. If you stand at Star here and you look at something that goes with 99.995% the speed of light, these beams come by you more than 15,000 times in 1 second. 15,000 times in 1 second, the beams are crossing in the Star experiment. So this is an enormous undertaking with more than 1,000 people in the accelerator facility itself to keep these beams happy and going for us experimentalists to do physics. Here are the sizes again: 1 mile in diameter, 2.4 miles in circumference. If you look at this at the Large Hadron Collider, the big feat here is that you can't build it above ground. So you're about 50 to 80 meters below ground, and everything has to be in the tunnel. And in that tunnel, you build 3 big experiments that do heavy ions, 1 dedicated to heavy ions, which is the ALICE experiment. And both ATLAS and CMS are also doing heavy ions. And LHCb is slowly starting to also do heavy ions, because even the high energy physicists recognize that heavy ions are pretty exciting to study. And it is really Einstein at its best, because if you think about it, what we accelerate is lead nuclei. They're made out of 208 protons and neutrons. That means you shoot effectively 600 quarks on 600 quarks. And what comes out of this when you shoot 600 quarks on 600 quarks is a fireball in the middle that spews out about 10,000 new particles. So energy that comes through the collision and is stored in this quark-gluon plasma, in this fireball, in the end turns into matter. And it turns into matter that has parts in it that are not seen right now naturally in the universe. And those are the parts that we're studying. So these heavy ions are very much contracted, Lorentz contracted, so they're not round anymore. They look like pancakes. This is just a schematic. In white, you see the neutrons. In red, you see the protons. But when you shoot those together like this is actually a picture that comes out of the star detector. These are, with this coverage, about 2,000 different tracks. Each particle leaves a track. Each track is curved because you have that amazing large magnet around it. Each charge track is curved. And that's how you find the momentum. And that's how you can identify the particles. And you can study those particles. And what we're really doing looks very much like what you've used to from NASA, when it shows you the slow expansion of the universe. It starts off with inflation, and then it expands out into the universe as we see it right now. The lower part is another picture of the cosmic wave, microwave background. And we're doing a similar thing. We're starting off with a very, very small system of deconfined quarks and gluons. And in the end, what we're measuring in our detector are actual particles. Now, this took 13.7 billion years. This takes about 10 Fermi over C, so about 10 to the minus 22 to 23 seconds. So what we're generating here lives very, very short. And we really will never see it itself. We will never see the plasma itself, but we see the remnants of the plasma. And what I'm showing you here is how the particles in a lattice QCD simulation actually form out of the vacuum when you let it run. And each of these blobs in the end will form a particle with a particle distribution that you can measure. And you learn something in the distribution of particles, and you learn something in what particles are coming out. Here is another way of showing this. You have a time scale, which is now, like I said, about 10 to the minus 22 seconds. In that very, very short time scale, the system starts off as quarks and gluons, which we showed partons. Then it hadronizes back into protons, neutrons, pions, and everything else that I will show you. And it does that at particular temperatures measured here in mega electron volts. And the whole system goes through a very, very violent expansion with an expansion velocity about half of the speed of light. And all of these numbers that I have on here were measured and calculated in different papers. And you see most of that happened between 2005 and 2010, 2011. This was really the discovery phase of the quark-gluon plasma at the relativistic heavy ion collider at Brookhaven. Besides the lattice QCD calculation, we found out that the things that we do actually behave like a fluid. And I come to that in a second in a little bit more detail. But here I show you a hydrodynamical calculation, not at the quark-gluon level, but at the level of protons and neutrons that are being collided when you have the collision at the relativistic heavy ion collider. And you see that they behave very, very homogeneously. They have hot and cold spots because the neutrons and protons are not originally homogeneously distributed, but then these hot and cold spots kind of go away and they form a blob that can be described hydrodynamically. And that is a very interesting feature of it. Many people said, is this something that we can also achieve by using very, very powerful lasers? rather than building another billion-dollar machine, can we do this on the tabletop with lasers? And we compared this in particular when the latest petawatt lasers came out. And this was a paper from 2006 at the time when we did our studies at STAR. And you see that there are temperatures quoted that you can achieve, there are intensities quoted, and there is this word that made us very interested, that they found plasma hydrodynamics inside shooting a laser onto a sapphire crystal. And we looked at these micro explosions and compared them, and it's really, really still quite different. And the main difference lies in the energy density that you can really achieve. The energy density that you can achieve with the laser in a spot, with the laser at the time, they are now even more powerful, but they were 20 orders of magnitude too small. And that leads to the fact that the temperature that you can reach is about 6 orders of magnitude too small. So no, this cannot be achieved just yet with a laser, and it will probably never be achieved with a laser. So this is really a laser that, when you talk about petawatts here, you need 20 orders of magnitude more energy density to generate it. So this is really still exclusively done in relativistic collisions at big accelerator facilities. So let me go through the discoveries in the last part of my talk, and then probably have a discussion with you. The first one obviously was the American Institute of Physics Science Story of the Year in 2006, was the fact that this quark gluon plasma that we found did not behave like a plasma, it behaved like a liquid. But it behaved like the most perfect liquid ever. That means the particles in it are so strongly interacting with each other that the fluid imperfections measured through the viscosity as a function of entropy went effectively to the string theory limit. So this is more perfect, less viscous by a factor 10 than superfluid helium. So generally you take superfluid helium as a perfect liquid. It turns out that ultra cold atoms are, almost a factor 2 roughly, even better than superfluid helium. But quark gluon plasma is again a factor 5 better than ultra cold atoms. But you have to see here that you're comparing system at the lowest possible temperature, 10 to the minus 7 Kelvin, to a system at the highest possible temperature, 10 to the 12 Kelvin. So matter behaves very similarly over 19 orders of magnitude, but it behaves the most perfectly like a liquid at the highest temperatures ever measured. That is an important feature because now you can say I can use hydrodynamics to describe what goes on in the early universe. That is not expected, and that is now being used very heavily to understand the formation of matter and the formation of galaxies in the universe. Because the matter does not flow as freely as we thought, because effectively you have a liquid drop at the beginning of the universe evolution, and you don't have a plasma that turns into a gas. So that thickness of the liquidity, that it's less viscous, but it's still a liquid, that allows you to calculate formation of objects, then stellar objects in the formation, in the evolution of the universe. And I come to that in a moment. How did we find this? We found that by making a collision in which the interaction zone is actually not spherical, but it's ellipsoid. And then we measured how the particles are emitted from that ellipsoid. If it would be a gas, they would flow in all directions in the same way. If it's a liquid, then it's easier for them to get out the short axis than the long axis. That means there would be an anisotropy in the momentum distribution of the particles. The particles that would go out the long axis would have a lower momentum because they interact more with the medium than the particles that come out the short axis. This is called the flow anisotropy, and the flow anisotropy can be measured by doing a Fourier transform of the momentum distribution in the angular space that you're having, and that Fourier transform gives you a so-called Fourier coefficient, and the one that you're interested in is the one for elliptic flow, because you generate an elliptic geometry the way you interact the two particles. And when you don't do that, you can see that this V2 distribution really can only be described if the matter that you had in this elliptic interaction region here was a liquid and not a gas. So it behaves with perfect hydrodynamics, and perfect hydrodynamics also is defined by the quantum limit, which is 1/4 pi, and that's exactly the value that you're getting for the viscosity over entropy if you calculate it out of these V2 components that you're measuring. But one more thing out of the V2, and that was very exciting for us too. When we measured these anisotropies before, they scaled with the mass of the particle. So if you take a pion, a kaon, a proton, a neutron, each one of them scaled perfectly with the mass. So you had to divide the V2 by the mass in order to have all of these curves that you see here fall on top of each other. Now what I'm showing you here is a distribution of mesons, pion, kaon, kaon, and a distribution of baryons, so 3 quark states, proton, lambda, and psi. And you see, whatever we do here, they do not fall on top of each other. We try to scale it with the mass. That brings us from momentum to kinetic energy. And then they fall on top of each other in the low momentum region, but they still don't fall on top of each other in the high momentum region. But then when we scale both axes with the number of quarks in each particle and the mass, you get a perfect agreement. So that is unambiguous proof that we have generated a plasma of deconfined quarks and gluons, because the quarks and gluons here carry the anisotropy and not the particles and their masses. It depends only whether you have quarks and gluons and not which baryon or which meson. You can see that here because these are all three, the 3 quark states, and these 3 are the 2 quark states. And if I let them fall on top of each other, just by scaling with the number of quarks, I get a perfect agreement. So this was really the discovery of deconfinement and the discovery of perfect liquidity. Let me move on with the next discoveries. The next one is the realization that when you shoot something together over such a small volume that is not perfectly aligned with each other, that means the 2 particles, let me go back for 1 second, the 2 particles hit each other like that, this ellipsoid does not only have an elliptic shape, it has a tremendous angular momentum. And it has a tremendous angular momentum over a very, very small, medium size, over a very small volume with many, many charges inside. So you're generating a huge magnetic field. That magnetic field is the largest one ever built, ever found, 10 to the 19 Gauss. The next largest one would be the huge magnetic field that you get in a very, very compressed star, like a magnetar. And there you get 10 to the 15 Gauss. So again, the microscopic system on the femtometer scale mimics the system that you have in very dense stellar objects. And that's very important to recognize. And this leads to interesting effects when you measure it in a liquid. You get so-called vorticity effects. It was in nature just recently, the subatomic swirls that we can generate in heavy ion collisions. And it really gives us a measure of the size of the magnetic field. This magnetic field is extremely unstable. It will decay away as soon as you come out of the quark-gluon plasma. So again, the fact that we can measure these vorticities in the quark-gluon plasma is another signature for deconfinement. Now I come to matter production, and that's the stuff that I'm personally very interested in. And the first thing was that we discovered antimatter, and there was a satellite shot up a few years before, the alpha magnetic spectrometer, that wanted to measure antimatter in space. Antimatter had not been discovered until 2011. And then we found it first, which made us very happy. But there also are now indications from the AMS experiment in space that they can find antimatter remnants also in space. What is important here in both of these instances is that matter behaves like antimatter. So up to this point, we had antiprotons, we had antineutrons, we had antiparticles, but we never were able to show that these antiparticles can produce antimatter in the same way that particles produce atoms, produce atomic structures like helium-3, helium-4. So Starr and now also Alice measured anti-helium-3 and anti-helium-4. And the interesting thing here is that the relative abundance of antimatter to antiparticles is exactly the same than the relative abundance of matter to atoms. So there is no reason, if you leave antimatter alone, that if you leave antiparticles alone, that they should not generate an antimatter system. And that antimatter system, as you can see here from the distribution, does not show any other features than the matter system. So you can drive that further. You could have anti-lithium, anti-beryllium. If you would have an anti-sun made out of antiprotons, you would form all the antiparticles in the same way that you form the particles. So if there's a decoupling in the early universe of matter and antimatter, then there will be an antimatter universe. That can be shown by showing how exactly linear this curve is with respect to this curve. So it's a very exciting discovery, and it now is effectively an antimatter factory, because we can make lots of antimatter at this point. Now lots is a little over the top. We made about 100 of them. So. How am I doing in time? I have 10 more slides. Is this okay?
Yes, sir, it's okay.
Good. Thank you very much. So it's a Nature article. If you want to look at it, it's very exciting. The other thing that I'm very excited about too is that we also overproduce strange particles. We produce particles that have strangeness in them. This was a picture from Alice just recently in Nature Physics that shows that the relative abundance of strange baryons made out of strange quarks exclusively, the omega baryon, SSS, is about a factor 3 to 5 higher than the abundance that you would expect if it just scales like a proton or a neutron. So you're overproducing strangeness, and on top of that, my group has shown that that strangeness comes out of the quark-gluon plasma at a slightly higher temperature than the protons and the neutrons. This change in temperature would mean that in the evolution of the universe, strange matter for a certain period of time is produced by itself without non-strange matter around it. And that might lead to strange matter formation, which then can find itself in very dense matter, for example, in neutron stars, and then survive in those dense stellar objects to now, to 14 billion years later. And this is what links us later on to the gravitational wave measurement. I showed the strange matter factory already. Now I go one step further, and I don't only make anti-matter or strange matter, I make anti-strange matter. So I make anti-hypermatter. So I take an anti-triton and I replace one of the neutrons inside with a lambda. An anti-neutron with an anti-lambda, and I make an anti-hypertriton. So now in the nuclear chart, I don't only find elements, I find elements where the neutrons are replaced by neutral strange particles, and these particles have a finite lifetime, and that finite lifetime, if bound to a metastable state, could potentially survive in certain configurations. And again, that might play a role in how we understand the core of neutron stars, because it could not only be strange matter, it could be hypermatter that governs the neutron star core. So I'm getting into quite exotic materials that are all being formed in this factory of heavy ion collisions that you see right now. Yeah? And then the last one that you might have heard about is multi-quark states that are allowed in the standard model but haven't been found, or hadn't been found, at least not unambiguously, until the LHC came around. So I'm showing here the measurement from LHCb because it's the most beautiful one. They've found pentaquark states, 5 quark states that are made out of these 5 quarks. Now, there is a big debate whether this is a molecular structure, as you see here, between a sigma and a D meson, or whether it's indeed a pentaquark where the 5 quarks live in one single blob. Only the future will tell us, but what we know already now is that these quark states that are made out of more than 2 or 3 quarks, that they exist and that we can find them. Everything we have found until now was in the charm sector, so they all require a CC bar pair, a charm anti-charm pair. And one of the big puzzles that my group is involved in very heavily is, why don't we see them in the strange sector? We found the hypermatter, we found the strangeness enhancement. Where are the strange pentaquarks? And this is a research that's going on very heavily right now. Let me show you, I don't want to overload you, but I show you 1 or 2 more points now from the experiments at RIC that have now purposefully gone to a lower energy. So everything I showed you up to now was done either at the highest RIC energy, which is 200 GeV square root of S, or at 5 TeV. But by having a very versatile machine like RIC, we were able to go to lower energies where we potentially might see a critical point. And we have indications, indirect indications up to this point, very active research going on right now with a very large Indian contingent working on this as well in the so-called beam energy scan runs at RIC. And what we know as of now is that there seems to be a softest point. Again, we find the softest point, the point of maximum compressibility of these 2 particles by looking at one of those flow coefficients that I showed you, not V2, but V1, and it seems to go through a minimum at about 10 to 15 GeV. And at that same minimum, we see huge density fluctuations in when we compare the product of tritons and protons to neutrons. What that is essentially is a neutron density measurement, and the neutron density fluctuates the most in exactly the same range of energies, which is also an indirect signature of critical behavior. I don't want to go so far as saying we have found a critical point, but if there is a critical point where our phase transition would turn from a crossover into a first order phase transition, it's probably in the region where we find these very anomalous behaviors. And this is something that we study with much better data now at RIC. There is a postulate from the lattice QCD calculations, and lattice QCD cannot go so far, so our theorists became very inventive and expanded the lattice QCD calculation to higher density, to higher baryochemical potential by using a holographic system. The holographic system allows you to do a semi-classical approach by treating QCD like a conformal field theory. It's something that Witten, Maldacena have proposed when it came to supersymmetry, and we applied this 5-dimensional theory now in order to expand our coverage in density to higher densities. And when you do that, you see a critical point, and you see a critical point at a temperature of about 80 MeV and a baryochemical potential of about 700 MeV. On this plot here, that would correspond to an energy of about 4 to 5 GeV. So it should be somewhere here, and the measurement would be that the fluctuations diverge at this point. This is a fluctuation measurement with the quality we have right now. You see there's an upswing, but it's not statistically significant by any means. And the measurements that we're doing this year and next year give us points in this region with an error bar on this scale of about 0.2 to 0.3. So it should definitely tell us whether there is critical behavior which could be linked to this postulated critical point, which would be very exciting. And this goes back into this holography. It's almost a little esoteric, so for aficionados of A, holographic ideas, B, supersymmetry, and C, string theory, I'll let you look at Juan Maldacena's Scientific American article and everything that has been proposed at that time. It was proposed very early on, at the time when we found the quark-gluon plasma already. You see this is from 2005. But, you know, linking Rig to supersymmetry is clearly not a trivial undertaking. And one also has to be honest that many of the minimally supersymmetric models that we had were really experimentally excluded by the first 10 years of LHC running. There has been really no experimental evidence for supersymmetry at this point. And it turns into something that, you know, can be almost certainly excluded as a valid theory within the next few years, I would say. So my final questions are still the ones of how does visible matter get its mass to this point? We have step one, but step two, we have to study what's going on during this phase transition. And then obviously, if visible matter is not exclusively made out of up and down quarks, can we link evidence from neutron star measurements to what we measure at the accelerators? And that is really the future. And if you see what has happened with the LIGO measurements, this is a schematic of GW170817, which was measured in August 27, and which was not a black hole merger like the one that LIGO measured its first gravitational waves on in 2015, but it was indeed a neutron star merger, so a smaller system, but a system that has different features than a black hole merger, but features that can be measured and identified through the ringing spectrum of the gravitational wave. If you put the data that we get from this into a calculation, you see that this simulation leads us to temperatures of about 30 MeV and densities that are the lowest densities that we reach in the fixed target experiment at the relativistic heavy ion collider. So there is a real push right now to go to lower energies, and FAIR at GSI, NICA at Dubna build smaller, cheaper machines, but in the range where heavy ion collisions could indeed link to what we see right now in the core of neutron star mergers. And that is obviously very, very exciting. One of the things you want to really study there is isospin, because you have a neutron system. You have almost no protons in the system. So what does isospin do when it goes through the phase transition? And how can we understand the formation of matter in the core of these neutron star mergers? I want to close with just some very broad picture where we have now recognized that the sector that was covered, when you look at all the forces that was covered by QCD, really is not a homogeneous sector, but it has perturbative QCD that can be very well described through simulations where you treat the interaction as a perturbation. So that is in the weak coupling limit. But then it has this QCD matter, which is strongly coupled QCD, which we measured, and which is difficult to simulate by looking at lattice, at least at a particular density, because of the sign problem that you're running into when you try to solve the Lagrangian. And in this QCD matter, it turns out that you can use thermodynamics, hydrodynamics to describe the system. So you have new and emergent phenomena that can be described by relatively basic physics on a macroscopic scale. So instead of looking at the quarks and gluons, you take a step back and you look at the matter and you define the matter through coupling, through temperature, through viscosity, through diffusion, and through conductivity. And indeed, the matter is so strongly coupled that the microscopic makeup is less important than the macroscopic features of this deconfined matter. And that's what you've learned to study. And then you look at the transition, and that is where you learn about matter formation, because you look at the quantum number dependence, you look at chirality and confinement, and you look at mass generation. And QCD and relativistic heavy ion collisions, and this is my last slide, they have come a long way by linking ourselves to astrophysics, to plasma physics, to many different types of physics. We actually have found a breeding ground where we have impact in string theory, in strong coupling theories that use supersymmetry, in quantum chromodynamics, in cosmology, and in plasma physics. So nuclear physics, this type of nuclear physics now sits at the heart of all of these different fields of physics. And I think I leave you with what I started with. I think both Drs. Thomas and Sudarshan would be very, very proud if they would be around right now and see what you can do with heavy ions at energies that are achievable at large accelerators. So thank you very much for the attention you gave me. I actually didn't look at my clock. I hope I didn't run over too much. Let me stop sharing, because then I can see my clock. I stayed, I think, close to an hour. Okay, I hope I didn't wipe everybody out. So I'm ready for your questions if you have any.
Can I ask you a very elementary question that is about blue balls?
Yes.
About 25 to 30 years ago, there were speculations that a state called blue ball might exist. What is the evidence for or against blue ball from your study of quark gluon plasma?
We are very, very careful with this. We're not quite ready to make an announcement, but we have states in the resonance states, in the mesonic resonance states, which look like blue ball structures of relatively few gluons. So you're not achieving large blue balls, but you get, for example, the F0 resonance, which we have measured, but we're still trying to see whether we can understand the underlying structure by looking at the different decay branches of the F0. But it could very well be a glue structure. It's not impossible that it is a gluon structure.
Okay.
It would be another type of exotic matter. Again, it's not excluded by the standard model. So it's very similar in that sense to quark matter on the pentaquark level. And what we see might also be gluons, let's say 5, 6, maybe 7 gluon structures, but not massive glue balls that you would like to see. But that's also a question of how rare they are and how high in mass they would go. You know, they will become very broad as a resonance, and then you can't really see them anymore.
And about the multivariant states, the evidence is possible, isn't it?
Oh yes. So what I have shown you were the main channel we're looking at right now is dibaryons, and the main dibaryons we're looking at are omega-omega states and proton-omega states, and we've done femtoscopic measurements on the proton omega and the proton psi state, which have shown just in the last 2 years that the potentials between them are attractive. And if the potentials are attractive and the scattering length is good, we should see a proton omega or proton psi dibaryon state. We're very actively looking for those. We don't have evidence yet, but again, they would be in the strange sector, and we don't see anything in the strange sector, and we have no understanding why we see it in the charm sector but not the strange sector. So we have to look more.
I request the students to switch on their camera and microphone and ask questions.
Kartik raised his hand. Yeah.
Hello, sir.
Hi. Hi, Kartik. I can see you.
Hello, sir. My name is Kartik.
Give me 1 second. Joseph, could you mute your microphone? Okay, try again, Kartik.
I will start from a basic question. So, how do you accelerate particles to approximately the speed of light in the Large Hadron Collider?
It's actually quite interesting because when you start, your particle is neutral. So you take a lead atom and you have to strip the first electron off of it for it to be charged, to be accelerated through an electromagnetic field, which is essentially what we're doing in the ring. But the first step is very, very similar. It's essentially blowing, it's very simple. It's essentially blowing a lead atom through a foil with a hairdryer. So you generate an airflow and you take that atom and you blow it through the first foil with a certain speed, and the outermost electron will strip off when you blow it through the foil. And you do that foil thing actually a few times until you reach lead 10 plus. And when you have lead 10 plus, then you can take the electromagnetic field that you're generating in the cyclotron, in the ring, and you can accelerate it through electromagnetic fields. And then you, again, every time it goes through a foil, it strips off electrons until it's naked, until it's lead 208 plus, right? Or it's actually 128 neutrons and 82 protons, so it's 82 plus. It's lead 82 plus. So it's a completely naked proton and neutron ion then, and then you just accelerate it by ramping up the electromagnetic field that you have in the circular beam. And the more you ramp it up, the more the radius changes when the energy goes up, and the more the magnet has to push so that it can stay in the ring. And that's the big feat of the accelerator. So you really start off with a hairdryer, but you end up with the most sophisticated racetrack that you can imagine. And like I said, 50,000 times a second. If you don't keep it on track, if you lose it, right? And you always lose some when it goes around. So generally, what we call a fill lasts for about 8 hours, and then you have to start over again because you lost too many of the ions, and you don't have enough to get good collisions. And then you have to fill again, and then you can accelerate.
Okay, sir. Thank you. Thank you.
Hello, sir.
Hello.
I'm Shalin. I'm Shalin Saji, the first year undergraduate in physics. My question is that we know that when particles collide with each other, nearly at 99.999% the speed of light, new particles like the Higgs bosons are produced. But these Higgs bosons were not present in the initial phase or in the existing particles. So how does these Higgs bosons just emerge from the existing elementary particles? What drives them to do so? That is my question, sir.
So just to make sure we understand, if you do a heavy ion collision, if you use the energy that the CERN can produce in order to accelerate heavy ions rather than single protons, the energy that every single proton carries is not enough to make a Higgs boson. So we do not make Higgs bosons in ALICE, for example. But you're right, we make Higgs bosons in ATLAS and CMS, because ATLAS and CMS uses protons and protons. So So the full energy is in the protons, and that allows them also to record way more collisions than we record with the heavy ions, because we have to build a different detector which is slower in recording the data than ATLAS and CMS. The Higgs boson that is generated by ATLAS and CMS is a pure question of how much energy you put into your fireball. So the energy, since the energy in the fireball that you make out of 2 protons is only distributed over very few particles, one of those particles could actually have a rest mass of 128 GeV, which is the Higgs boson's rest mass. That particle is not made out of quarks and gluons. That particle is actually not it's an elementary particle, but it's not a fermion. So it's not a proton, neutron, or electron. It is a boson. And generally, these bosons are the propagators of fields. So the photon is a boson. The WZ bosons are the electroweak propagators of the electroweak field. And the Higgs boson is the propagator of the Higgs field. So as far as we know, it doesn't have an inner structure. It is an exchange particle that the Higgs field actually exchanges with the quark in order to give the quark mass. And therefore, we will not be able to study its structure, and we will actually not be able to make it because we don't have enough energy to make it in ALICE. You need the 128 GeV rest mass in order to make it. And that was the interesting thing, that Fermilab just had too little energy, just a little bit too little energy to find the Higgs boson. But we knew that if we would build a bigger machine, like the LHC, it would be able to find the Higgs boson, and found it within the first 2 years. So that was pretty exciting. I hope I answered your question, Shalin.
Yeah. Thank you, sir. Thank
you. Hello, sir. I'm Navami.
Hi, Navami.
Hello, sir. So I recently completed my master's in applied physics from CMS College, and I'm interested to join for the PhD course at Houston University. I'm in the process of applying for the same right now.
Very exciting. Yes, we're looking forward to seeing you in our application. Are you trying to come in 2021? Is that your plan?
Yes, sir. Yes, sir. 2021.
Okay.
Right. So my question is, how can the physics of heavy ion collisions shed light into the transition of quark-gluon plasma to matter as we see now, to the universe and life?
Well, I hope I answered some of that in my talk, because that was essentially the basis of it. I think what you learn is what type of matter, besides the normal matter like protons and neutrons, what type of matter has formed in addition to these types of matter very early on in the universe. And can we therefore deduce from this early matter what happened in the evolution of our universe in things that we cannot probe easily on this planet, like neutron stars, the inside of neutron stars, potentially this idea of an antimatter universe where, so one thing that I mentioned only in passing is that there are, and this is a little controversial right now, and it's very much studied, but there were antimatter candidates, anti-helium candidates were found in space by the alpha magnetic spectrometer. Very few particles, maybe 2 or 3 of them. But if they are at all in our universe, then the question is, where did they come from, right? So there could be potentially, at least in the far away part of our universe, isolated antimatter. And what we have shown with our studies is that if antiparticles can be left alone and do not annihilate by meeting particles, if they're just antiparticles hanging around, they can form antimatter. And then that antimatter could form anti-whatever. Anti-life, potentially. If you can do anti-oxygen, you can do anti-helium, you can do anti-nitrogen. Right. We're made out of matter. Could we be made out of antimatter, right? So this is a very speculative question, but the basic block that we have shown is that particles can form matter on the anti-particle side. And that's very dramatic and very fundamental.
Okay, sir. Thank you.
Thank you for the question. Good question.
Thank you, sir.
Hi, sir. My name is Priya Dushan. I'm a second-year postgraduate student. Sir, my question is, what is the difference between the number of participants and the number of binary collisions in heavy ion collisions?
That's a good question. The number of participants is the idea that when you have a particle, a proton or a neutron, as soon as that proton or neutron is hit, it cannot participate again in another interaction. So it looks at, and this was actually an idea by Roy Glauber, which is called the Glauber model, which has nothing to do with the Glauber-Sudarshan representation. It's a different part of Roy's work, but it essentially says if you collide protons and neutrons, you cannot look at their inner structure. You can only look at them as one particle. And generally, the participant scaling works well as long as the energy is low. So essentially, when a proton hits another proton or a neutron, we call it wounded, and a wounded nucleon cannot hit another proton or neutron to the same degree than it hit the first proton or neutron. So you take it out of the interaction, and that is participant scaling. So ultimately, the maximum you could have is 208 plus 208 participants. That's 516 participants. Binary scaling says a proton is made out of 3 quarks, and another proton is made out of another 3 quarks. So if 2 protons hit each other, there are 3 possible collisions and not 1 possible collision. So to a simplest effect, binary scaling is 3 times as large as participant scaling. And binary scaling works very well when the energy that the proton carries is very high. So the high momentum particles that come out of an interaction scale binary, whereas the low momentum particles that come out of an interaction scale with participant scaling. And it's a big debate in our field whether this is too simple-minded by saying at low energies the protons hit each other, and at high energies the quarks inside the protons hit each other. But it's true that in order for the quarks to see the quarks in another particle, they have to penetrate. And in order for them to penetrate, they have higher energy. If they have low energy, then they effectively, the 2 nucleons just bounce off each other rather than penetrating each other. But at the LHC, the energy is so high that the particles actually go through each other and don't even stop each other. The only thing that they do is they deposit energy. But the baryons, the protons and the neutrons, carry the baryon number, go forward and backward, and leave your detector and are not inside your detector. Your detector, the fireball in your detector is pure energy. There's no particles in it. And then this pure energy converts into particles at the phase transition.
Thank you, sir.
Another good question, Gia. I like it. Very good.
Hello, sir. My name is Zainaba Harris. I am a second-year postgraduate student. My question is, what are the possibilities of quantum entanglement in the initial and final states of heavy relativistic ion collision?
Wow, what a great question, Zainaba. I love that question because that is a field of research that I just started with my group a year ago, and it is very, it's a little speculative. It is very difficult if you have a very large system to look at this large system as a quantum entangled system. Because generally, when particles interact, the common wisdom is that as soon as you have an interaction, the initial entanglement gets lost. So there's this effect of decoherence where even if they were entangled in the beginning, as soon as you make a strongly coupled system, they're not entangled anymore. So the memory of the initial system is lost. Now, I don't believe that. I happen to not believe that, right? There was a very exciting study that just came out in Nature about 6 months ago where somebody showed, I think the first author was Kang Hong, that you can have an entangled system over a very large number of particles, a ultra cold system, one has to say, but over a large number of particles and at a very high density. So we are an ultra hot system over a very large number of particles and high density. But I believe that entanglement could survive the quark-gluon plasma. And then the distributions that we see of particles after the phase transition would be not driven by thermalization, but it would be driven by quantum entanglement that mimics thermalization. It's a huge entangled system, but it is not a system that interacts so much that it thermalizes, but it's a system that has features in it of the original entanglement. And if I can show this, then I can, for example, show that if I make a multi-quark state, like Dr. Babu asked, where he said, you know, what about a dibaryon? Or what about a pentaquark state? With entanglement, I would be able to show that these 5 quarks that make a pentaquark state, or these 6 quarks that make a dibaryon, would come all out of the same string, out of the same entangled quark-quark state that I have in the interaction. So a quark hits a quark, it makes a string, and all of the quarks that come out of that string are entangled with each other, and that entanglement is carried all the way through to the final state. If we can prove this, then we would have a quantum mechanical description of a quark-gluon plasma, which we definitely do not have right now. Right now, we use quantum chromodynamics in a very isolated way. We treat each quark-quark interaction as a quark-quark interaction in vacuum, which is clearly not true, because that quark is part of a huge conglomerate of quarks and gluons. So why would you treat it as a single quark? So it goes against any quantum mechanical description what we're doing right now. So if you would give the problem of the quark-gluon plasma to Schrödinger, he would tell you it is entangled to the highest degree, and entanglement that drives all the features that you see in the particle production in the universe. We haven't proven that yet. There are indications, there are things that people have suggested to show that this is the case, and it's something that we want to measure in the next 2 years, 2-3 years at the LHC. So if you join our program now, we're working on entanglement for the next 2 years.
Thank
Good
you,
question.
sir. Thank you.
Good question. Thank you very much.
Thank you, sir.
Hello, sir. I'm Georgina Maria Roy. I am a postgraduate student. My question is, can quark-gluon plasma be treated as the primitive particle soup of the early universe?
Yeah, I think it can. I mean, you know, Frank Wilczek wrote a famous piece once where he says it cannot. But I disagree with him on this one. And it's just different whether you look at it at RIC or at the LHC. What you achieve at the LHC is, like I said, the energy is so high that none of the original particles actually stay in your detector. They fly through each other and they go out of your detector. What is in your detector is pure energy. And that pure energy, that is the state of the universe at the phase transition, at the Qcd phase transition. If the protons and the neutrons that you have in the beginning when you shoot lead on lead, if they would stay in your detector, then you would have an imbalance between particles and antiparticles. But since they leave your detector, what we measure is that the number of particles is exactly equal to the number of antiparticles. And even more so, the antimatter particles are exactly equal to the matter particles. And that is exactly what we believe happened at the beginning of the universe. So there are studies now to be done about CP violation and all these things, whether we can show that how the matter universe decoupled from the antimatter universe, and that will probably not be done with heavy ions. But what you can see with heavy ions is that matter behaves like antimatter, and that's exactly what the early universe is expected to show. So yeah, it is the state. We make the right state. It's the state to study. Thanks for the question.
Thank you, sir.
I see a lot of young female students, so are there also some male students in India? Everybody is female. I like that a lot. I think that's very interesting.
Hello,
Go ahead,
sir.
Reshma. Yeah.
Hello, sir. Hello, sir. This is Reshma Elsa Biji. I'm a second year PG student. So my question is whether antimatter can form in the universe just like normal matter?
Yes. Yes, I think so. I mean, I think, I think we've shown this. The problem is, Reshma, that we don't understand the decoupling, right? We do not understand where the antimatter went. So what I have shown you is that I make as much matter as antimatter. If I leave that system alone, the matter will annihilate the antimatter. There will be no matter left, no antimatter left. There will be only energy left. So the problem that we're facing right now at the LHC is how can I decouple the matter from the antimatter? Where is the antimatter, right? So if this is indeed the state that has been formed, we cannot find the antimatter, but we can show that it has been produced. So we have shown that it is produced in the universe, but we don't know where it went. So now baryogenesis, the way it's set up, could potentially lead to this very slight imbalance. And you could make the argument, if you make such a small system, which is on the femtoscopic scale, with so few particles, you might not be sensitive to this very, very small imbalance between matter and antimatter, which over 14 billion years led to matter dominance and disappearance of antimatter. But we don't have the mechanism. We cannot say that. We can just tell you that we produce antimatter just as much as we produce matter. So another mystery for the next 100 years or so.
Thank you.
Thank you.
Thank you, sir. Thank you.
Thank you, sir. Thank you for enlightening us about antimatter in space, multi-quark states, and how we can peep into the early universe using these particle colliders. And thank you for answering the question, sir. Thank you.
Thank you very much. Thank you for having me. I really enjoyed it. It was very interesting. I got a lot of good questions, so I think you have a very good team of students there that you can be proud of.
Yes.
Very good. Thank you.
The link for the feedback form is shared in the chat box. Please fill it up and you will receive the certificate of participation. Now, I request Professor Matthew C. Matthews, former head of the physics department, to give the felicitation speech.
Hello. Can you hear me? Hello.
Yes, sir.
Hello.
Sir.
Yes, sir. Yes, sir.
Can you hear me?
Yes, yes.
Yes, sir.
Dr. Varghese C. Joshua, Honorable Principal of Cms College, Dr. Renu Jacob, Head of the Department of Physics Department, the Chief Guest, Dr. Rene Belvi, Dr. Rajan K. John, faculty and students, Dr. Babu Joseph Sir, Dr. Umman K. Varghese, guests to this program. See, it is interesting to see that one of the students attending this program has decided to join Houston University for higher studies. Dr. Belve inspired him to do so, and many students were triggered to answer very, very relevant, interesting questions. Thank you, sir. Thank you very much. Then I am thankful to Dr. Renu and the faculty for inviting me to this webinar to say a few words as a representative of the retired teachers, and I am privileged to do so. I remember the formation days of the trust and the activities carried out during the early years. Those days were really festivals and celebrations for our department. Dr. Umman K. Varghese, attending the seminar, also shared the joy in organizing such programs. We, the then junior teachers of the department, were entrusted with the academic components of the activities, and the seniors with the administrative part. The objective of the George M. Thomas Endowment Trust was to create and inculcate a scientific temper in students, because George M. Thomas sir was always a man of scientific temper. It is very important these days, because it is so sad to see that big organizations and responsible people meant for promoting scientific temper seem to deviate from their goals. Dr. George M. Thomas sir served CMS College as the head of the department, principal of CMS College, and as manager for a period. But he is remembered as a great teacher, a true academician, and a physicist to the core. He was really a genius without comparison. He was just and impartial. He had a genuine passion and love towards physics. His timely humor is also famous. His students list include world-renowned physicist Dr. Qcd Sudarshan, and one of the top Indian theoretical physicists and former Vice Chancellor of Cochin University, Dr. K. Babu Joseph. In many occasions, we have witnessed Dr. Qcd Sudarshan kneeling down on the feet of Dr. George M. Thomas, offering him a pranamam. Both these alumni found a real teacher in George Thomas. Whenever possible, they express their respect and reverence to Dr. George M. Thomas sir in their speech as well as in their articles. I am very happy to see that Dr. Babu Joseph sir is also attending this meeting. Once again, I am privileged to sit in his class, in this class of a great motivator, Dr. Babu Joseph. Students of George M. Thomas sir spread many stories about him. A small story is like this. One of the students, while doing an electrical experiment, found some smoke in the setup. He rushed to George Thomas sir and said, "Sir, experiment aga pugayunnu." Sir replied without any anxiety, "Pugayimadu, pugayim. I square RT alle, pugayim." This answer contains everything. This equation contains everything. It tells how to put off the smoke and identify and regulate the parameter responsible for the smoke and set it for a consistent and stable conduct of the experiment. George Thomas sir was not my former teacher, but I respect him as if he was my teacher. Any physics-loving people on those days used to do so. I congratulate the organizers of this webinar and wish and pray all success in the coming days. Thank you.
Professor Rene Belby has promised to show us an animation video. So I hope he'll be starting it right now.
I have promised you an animation video.
That's what I understand, sir.
I'm not
sorry
sure
if it is not ready.
I'm not sure what you're
Then it's
referring to.
fine, sir.
I have a little clip that we did in a movie that if you would like to see that. Let me see whether I can actually share this. I'm not really sure what you're referring to, so let me see whether I can bridge it a little bit. What has happened at CERN was that we had an accident the very first year we ran. You might or might not have been aware of this, but we wanted to start running in 2010, and we ran actually for about 2 minutes, and then we lost the beam because we steered the beam in the wrong direction, and it blew out quite a few of the magnets. And in order to fix this, we had to go down for 1 year. It took us 1 year to repair, but since then we're running without any problems. But that year was interesting because Hollywood came to us and said, we would like to make a movie. Movie is called Angels and Demons, and it's a famous book by Dan Brown, and it starts at CERN where somebody steals antimatter and makes a bomb out of it. And so Tom Hanks was in the movie. He was the main actor, and Ron Howard, which is a very famous Hollywood director. So they all came out to CERN in order to make that movie. And our room down in the tunnel was the best room out of the 4 rooms that is down in the tunnel. So they filmed the first few minutes of Angels and Demons at CERN in downstairs where Alice is located. It is quite unrealistic because when the beams are running, you cannot be down there. It's too radioactive, so you have to be above ground. And but they wanted to film down there, so there was no beam. But then it's Hollywood, though, they can make their own beam, they can mimic the beam, and they made the movie. I have that clip of the movie if you want to see that, but that's the only animation I would have. If you're interested, I can play it.
Yes, sir. Please.
Yes. Okay. Let me see what I can. Give me 1 minute. I'm not really sure that I can share that part of my screen, but let me try. I don't know whether my I presume my speaker will pick it up. Let me see. Takes a little bit too long. Okay. Now let me see whether Human was right and I can actually share this. Maybe I can share. Can you see this?
It's coming. Yes.
Is it full screen? Can you see it?
Yes, we can see the screen.
Okay, so this is actually, let me give you a short introduction. It's only 1:46 long. This is the actual control room of Aline on the level of the level of the detector. So this is about 70, 80 meters below ground. The actual control room that you're using when you're running the experiment has to be above ground. But it is the control room that we use in order to calibrate our detectors and so on and so on. And they did a very nice animation So I'm running this, and if you have questions afterwards, I'm still here. Let me run it and let me see that you hopefully also pick up the voices a little bit. So that was the movie. I don't know whether you saw.
Okay, thank you, sir.
And so if you have questions, a lot of it was correct. This was the accelerator, this was the beam, this was the detector. So I'm not sure how much of it you could see. If you haven't seen it, watch Angels and Demons. You only have to watch the first 10 minutes. The rest of it is not so exciting. Good, thank you.
Thank you, Dr. Tejal Abraham. A warm morning to our most valued chief guest, Professor Reni Billy, respected principal, former Cochin University of Science and Technology Vice Chancellor, College Bursar, head of the department, our senior teachers, faculty members from other institutions, GMT trust members, department alumni members, friends, and my dear students. It's my privilege to deliver vote of thanks on behalf of GMT Endowment Trust. First of all, I would like to propose hearty vote of thanks to our chief guest, Professor Reni Billy from United States, who gave his vital time from his busy schedule to grace this memorial lecture. Thank you, sir, for your very interesting and thought-provoking address. I am sure that our students are inspired by your thought-igniting lecture. Thank you, sir. I would like to extend our gratitude to our principal, Dr. Varghese Joshua, for his presence and constant support for all the academic activities of our department. I would like to extend thanks to our beloved alumni, Professor Babu Joseph, former Vice Chancellor, Cochin University of Science and Technology, for becoming part of this program. I would like to thank another our great alumni, Dr. Umman Varghese, for introducing the chief guest. Thank you so much, sir, for your constant support. I thank Bursar, Reverend Jacob George Achan, and former HOD for Professor Matthew C. Matthew for all your guidance and support. I would like to thank our beloved HOD, Dr. Renu Jack, for initiating this great event. I thank all the faculties from other institutions who participated interestingly and making the event success. I would like to thank my colleagues, senior teachers, GMT trust members, department alumni members for making this kind of lecture a great success. Finally, I thank all the students for showing their interest in this program. Thank you again for making this event successful. Thank you, sir.
I hope all of us enjoyed a very informative session. I thank everyone who attended the seminar. A special thanks to Professor Rene Belville. We hope he'll bestow us with the same privilege in the future. Thank you, sir. The session is concluded.
Thank you very much. Thank you very much for inviting me.
Thank you, sir. Thank you. Thank you, sir. Thank you. Thank you. So thank you very much for sparing your valuable time. Hope we will have more opportunity with you in the future. Thank you, sir. Thank you.
Thank you very much.
Ummen Verghese sir, also we thank you on behalf of department. Thank you, sir.
Okay, I'm hanging up now. Thank you. Bye-bye.
Thank you, sir.